Hello everyone, this is the class of ECE418 Statistical Signal Processing. We go back to online again because the weather condition. Today is like a storm, snows, a lot of snow here, and we have to go back to online. And okay, it's ECE418. This is the fourth week, Wednesday's class. Okay. Alright, last time we introduced the random variables and the random vectors, right? Several random values. Okay, let me review something here firstly. For random variable, x, we can have distribution function actually probability distribution function. Okay, probability distribution function. This is a f x of x equal to the probability of the event x smaller than or equal to lowercase x. Okay, so this is a function on this lowercase x. Then for discrete type, we have a list of the probabilities. We have x and the probability. Here I list the values alpha 1, alpha 2. Well, depend, right? Depend. Maybe like if you have dice, the total you have 6 numbers, and some other experiment maybe you have more samples, maybe even infinite possibles, right? And each value here, alpha 1, alpha 2, you have probability like p1, p2. In general, like alpha n here I write as a pn, maybe more, infinite, right? Like this. And when you have this one, you can have the you can have the distribution function. The f x of x will be the summation of those pi, those pn, so that those n, so that alpha n is smaller than or equal to this given x. For example, you have, if x is here, x here, all these are smaller than x, then you add these bit together, add this value here. It's the value of the distribution function at this x. Yeah. You can also have a graph, right? Okay, so this is discrete type. Yeah, the graph looks like this. You have alpha 1, alpha 2, and so on. Each one you have a value depend, right? This is x, right? The PR probability is here. Then CDF, this CDF distribution function, you still have alpha 1, alpha 2 until like alpha n, some alpha n, or maybe more. Yeah. Then each location you have a step here, and this step are just these values. Here's a p1, p2, here's a p1, here's a p2. Got it? Yeah, this is p2, this is p1. Here's at alpha 1 you have a jump, like here you have a parse here. The parse peak value is p1. Now here you have a jump, the step up, this step is p1. And at alpha 2, here's a parse, here's a step up by this p2. Right? Then keep working on. And finally, the final value will be 1. Final value will be 1. All of these summation of all these alpha n's will be 1. Yeah. So this is a discrete type case. And then for continuous type, we need It's similar with the list of the possible values, but now you have an interval, so we use a density function. We have a probability density function. Which is with your lowercase fx to denote it. And if you want to have a definition, it will be a limit of dirt go to 0, turn to 0. The probability of an interval with length dirt and contain x. So I think I can, like x minus x absolute value no more than dirt over 2, right? Suppose this is x. Then here's a dirt over 2. Here's another dirt over 2. Right? Totally is dirt. Then you check the probability of capital X inside this interval. You have probability over the length of the interval. So we'll call this the density, right? The density. For this density, you can have the distribution function fx of x or equal to the integral from negative infinite to x. Here's a fx of x dx. Now I have both. Okay, notation are same. I put the hat here. Alright. Yeah, this is the integral, the variable for the integral. This is the limit of the integral, right? Negative infinite to x. Yeah, this x is the same as this x. Right. This x hat only used will be only used inside this integral. Alright, this is one side, and another direction is, of course, we know the integral and the derivative, they are like a dualities, right? Duals. Okay, this one is derivative of fx of lowercase x. Alright, so we have both. We have both equation relation. If you know the distribution function, you take derivative, you have density. If you have density, you do integral, you have the distribution function. And with these functions, if you want to find the probability, okay, this one is easy, right? You want to find the probability, you just add the related terms together, add the pi together, you get the probability. And for this case, you need some like an integral or something. So we have this, the probability of a smaller than x smaller than b or equal to integral from a to b, the density function, to integral, or is f capital X of b minus capital F x of a. And this interval, or a smaller than x smaller than b, a smaller than x and x smaller than or equal to b, or a smaller than or equal to x smaller than b. Yeah, either way are same thing. They have same probability. The difference between these, now I have 4 different kind of interval, right? The difference is just in the both side, both end. You have equal or do not have equal, have equal or do not have equal, right? So the difference between these 4, just at most these 2 points, right? If you compare here, you have one difference here. This equal, this is not equal, right? At most both. Like here both are equal, here both are not equal, so the difference are just 2 points. But for this kind of random variable, the probability of 1 point is just 0, right? Totally infinite possible. So 1 out of infinite, that's always 0. So you add or remove 1 point here, doesn't matter. The probability is the same. So we no matter this event, this one, or this one, its probability can always be calculated by this integral or just a subtract of the distribution function. Okay, so this is for a single random variable. And then we consider a random variable with several random variables. We consider random vector. vector x equal to, okay, I write in a row vector. Okay, the column vector need occupy more spacing, x1, x2 to some xn, like this. Then we also have the probability distribution function. Probability distribution function, we use the same notation, capital F, capital X of lowercase x. But now capital X is a vector, right? So I can also write in this way, x1, x2 until xn. And this lowercase x is also a vector, x1, x2 until xn. I write in this way. And what is the meaning? The meaning is the probability of, we want every x1 smaller than x1, x2 smaller than equal to x2 until xn smaller than lowercase xn. So this is the definition. This is the definition of the distribution function. Okay, and similar we have the PDF, density function. Density function is a lowercase f x1, x2 until xn. Here's x1, x2 until xn. This one, it will equal to the derivative, okay, n times on capital F x1, x2 until xn. Here's x1, x2 until xn. Here's a partial x1, partial x2 until partial xn. Alright, you take derivative n times for each variable, right? Or the derivative on each variable, so totally n times on this distribution function. Then you have the density function. And the reverse direction, this f x1, x2 until xn, the distribution function, it will equal to the integral of the density function xn. Here's a x1 until xn, and dx1 until dxn. Here the integral from negative to positive infinity for all of these x1 and xn. Okay, so this is the density function. And if you want, make sure you are considering more than just one variable. You have several variables, several random variables here. You can add a joint in front of it. Joint distribution function and the joint density function. Alright. So this is for the random vector or several random variables. Okay. Let me see. I have one page. I have, where I put it? Oh, I see. Okay. Now this one, the probability. Okay. Then we consider we have several things related, right? Those parts, they are kind of basically. Now we can have some change. We start from that joint distribution function, joint density function. We can have the marginal distribution, and okay, before that, let me do something on it. Yeah. Okay, the marginal distribution function. Marginal density, we just consider density is fine. Marginal density function. just for two random variable, two-dimensional case. For high dimensional is more complex, but the meaning are similar. You see, f x1 of x1, this is PDF density function, marginal density function. It is the integral of f x1 x2 and x1 x2 dx2, and x2 run from negative to infinite, negative infinite to positive infinite. We do the integral on x2. So after the integration, this is just a function of x1. It is just the PDF of x1. And similar, we have f x2 of x2. This is also integration from negative to positive infinite of the joint density function, but this time on the variable x1. So after we do the integral, we have get x2 left, right? This is a function of x2. It's a marginal distribution. And then we can have the conditional distribution, PDF. We're writing this way: f x1 on the x2. Here's a x1 on the x2. This equal to, remember the conditional probability, it is a numerator over denominator. Numerator is a joint, is an intersection of two, right? So now x2 equal to x2 is a condition. It's condition. So this is the PDF of x1 under condition x2 equal to x2. Alright. Okay. Then the intersection will be, numerator will be intersection of both, right? Of these two. So x1 equal to x1 and x2 equal to x2. So this is just x1, x2, x1 and x2. And the denominator will be the condition, the probability of the condition, right? So this is the probability of this condition from negative to positive infinite. This is a f x1, x2, x1, x2, and we want x2 is fixed. So this is a dx1. Oh no. Yeah, dx1. So here x2 is fixed as a condition. So x2 is fixed. Right? X2 is fixed, a given number, a given value. So numerator, you have x2 fixed, and x1 is a variable you can change. This is a numerator. And denominator, x2 is fixed, and the x1 is used in the integral. So after this, you get just the number. This is number. This number, actually this number, you can think this is the probability of x2 equal to x2. Just things like this. But not exactly. Maybe you need to do two integrals. Yeah. But the meaning is like that. I just say this is the meaning like this. Alright. And similar, we have x2 on the x1 as a condition. f2, x2, x1. Then symmetrically with this, you just change the change x1, x2. But for numerator, it's the same. Numerator is same, still this. And denominator will be integration of f x1, x2, x1, x2. Now here's dx1 change to be dx2. Okay, so this is a conditional PDF. So when you have a joint PDF, joint distribution, then you can have the marginal density, marginal distribution, and the conditional PDF, conditional distribution. Alright. Okay, then next we consider those average values. Average values. Average values. Remember what kind of average values can we have? We have variance of x. We have mean value of x, the variance of x. Right? We have this. Now we have a joint distribution. So we have x1, x2. Then we need a similar thing. Okay. So things like this. ex1 equal to integral of x1 times f x1 x2. Here's x1 x2 dx1 dx2. Yeah, both. And here's both x1 and x2 will run from negative to positive infinite, like this. And similar, ex2 is also integral, and inside now is x2 times f x1 x2 x1 x2 dx1 dx2. Now we always have this. And actually we can have more general case. If some y equal to function g of x1 and x2, that means you can build another random variable based on x1 and x2. Add them together, times them together, times some sine cosine with some square or login or exponential powers, any kind of function. G could be any function. Then you can build another random variable y. Okay, if you want to find the density function of y, usually that is hard. But if you just want to find those average value, then we can have the average value of y will equal to the integration of g of x1 x2 times f x1 x2 of x1 x2. Oh, here it will be lowercase. Okay, lowercase. And dx1 dx2. Here both x1 and x2 will run from negative to positive infinity. So we have this one. We have this one. Then you see, this is just g is x1, right? G is x1. Here's g. Second case, g is x2. G is x2. Right? Okay. Then we can have more general case. Now we consider the variance of x1. By definition, this is expectation value of x1 minus ex1 take square. Right, this is definition. We have variance of x1. Now how to calculate? You see, now g is this part. Right? Y is g, right? This part, this is inside, this y, this is g, right? This is g, so this is g. Now you replace g by this, then you can calculate. So this one, it is equal to the integral of x1 minus ex1 square times f x1 x2 x1 x2 dx1 dx2. Negative to positive infinite, negative to positive infinite. So you can have this. But usually this is long calculation. So people like you this way. This equal to e of x1 square minus ex1 square. This is the formula. Usually this gives us more convenience to calculate, shorter time. All right. And similar, we have variance of x2 or equal to expectation value of x2 minus ex2 square, which is e of x2 square minus exi squared in outside. Yeah, both square, but the location different. This is square of x2. This is square of the whole. This is x2, sorry, the whole E of x2. This is the variance x of x2. This is variance of x1. Right. Actually, these two formulas, this formula you can apply not just for this case. Here we have a joint distribution of x1 and x2, right? Two-dimensional case. For one-dimensional case, we have similar way and the same formula, right? Remember that? Yeah. Okay. This is a variance x2, and then we can consider the kind of joint thing. So covariance of x1 and x2. That is COV of x1 and x2. It is defined as expectation value of x1 minus EX1 times x2 minus EX2 with conjugate. Alright, it's like this. Let me see. Yeah. Conjugate. Yeah, we can write it in this way. Okay. If it is a real case, then it doesn't matter, right? This is covariance of x and y. And then we can have a formula. This is a E of x1, x2 minus E of x1 times E of x2. This is similar with this, right? Similar with this. Here's EX1 square. Now is EX1 times x2, right? You times these two together. And here's EX1 square. Here's EX1 times another EX2. So similar. We have similar formula. This is covariance. Alright. Okay. Covariance. Alright. And another one. Okay, this one. This is a correlation of x1 and x2. It is just we denote it as R x1 x2. It is just E of x1 times x2 conjugate. I put it here. This one can be applied on both complex number or real number. Okay, so this is a correlation. And we have another one. Correlation coefficient. It denotes as rho x1 x2. It is covariance of x1 and x2 over square root of variance of x1 square root of variance of x2. We have this. This is a correlation coefficient. The name, you see, these two are somehow confused. A coefficient of x1 and x2. Yeah, you should remember which is which, because they have a common part. Both are correlation. This is just correlation, but this is correlation coefficient. The rho is a correlation coefficient. And we have a property. This rho x1, x2 take absolute value will be a number no more than 1. So another word is rho is a value between negative and positive 1. And we have this. This is a property for the rho, the correlation coefficient. Right. Okay. Then based on these, we have several different kind of relation between x1 and x2. Some relation. Between x1 and x2. If the joint density equal to the multiplication of marginal density function. If we have this, we call this as x1 and x2. They are independent. Alright, this is a similar way that, okay, you can see this one, the joint, the marginal distribution, with the marginal distribution. I put it, sorry, I can't find it. The marginal distribution. Okay. This is a sorry, I put this somewhere. Okay, anyway, yeah. So this case, if this one can separate, the joint density can separate as a multiplication of 2, then we call them, they are independent. Okay, actually you can check this one. In this case, fx1 under condition x2, x1 under condition x2. By definition, we have this, right? fx1, x2, x1, x2 over integral of fx1, x2, x1, x2 dx1. Right? We have this. But now, this one can be written as this, and this one can also write in this way. Both can write in this way. Then you can. This is the integral for x1, so you can remove fx2 term out the integral. And denominator, you also have a fx2, right? You have a x2, the multiplication. So x2 term you can cancel. This will become fx1 x1 over integral of x1 dx1. You get this. And this, we know the denominator is 1. This is always 1, right? Any density function, you do the integral over the whole sample space, you get 1. Now this is the integral on whole sample space, then you get 1. So this is just on the condition x2, the conditional probability density, and this is just the probability density function itself. They are same. So do you have the condition or do not have the condition on x2? Doesn't matter. This is independent, right? This is independent. Okay, this is 1. And the second kind of relation, if this is ex1 x2 equal to e of x1 times e of x2. In this case, we call it uncorrelated. X1 and x2 are uncorrelated. And the third case, if e of x1 times x2 is 0, then we say x1 and x2, they are orthogonal. Yeah, it's orthogonal. Alright. So this is the relation between x1 and x2. And I think I have a property. Do I give that property? Yeah, I gave this property. Okay, now for the joint distribution of x1, x2, x3 until xn, we can have like the covariance of xi, xj for I run from 1 until n. J also run from 1 until n. Yeah, we have this. So we have a matrix. The covariance of x1, x1 until covariance of x1, xn. And second row is the covariance of x2 with x1 until covariance of x2 with xn, and so on. The last line will be covariance of xn and x1 until covariance of xn with xn. Yeah, this is a matrix. This matrix, which is called the covariance matrix. And property here I denote as just a cx. If this is a capital X equal to this, cx, capital C, use a capital C x for this covariance matrix, or covariance of capital X, like this. You can write in this way: covariance of X equal to expectation value of X minus EX. Now this is vector, this is also vector, times X minus EX. I need this is a column vector, this is a row vector. So if I write X in this way, then this one will be, you need to add a transpose. If here you write as a column vector, then transpose will be here. Alright. Yeah, it depending on your way to describe it. Now I use this as X, then here's a transpose here. And in complex case, you also need a conjugate here. Alright. Yeah. So this is a matrix, covariance matrix, and the property is like this. The covariance matrix X is positive definite, and symmetric. It's a symmetric and a positive definite matrix. Remember what it is? We just learned this from the first part, right? So we have this matrix. It's always like this. Okay, this is in generally, and we can also have another matrix that is just this one. Another matrix. This is a correlation matrix. This is covariance. Another one is a correlation matrix. This is a Rx equal to E of X times X. If this is a row, I still need a transpose here and maybe a conjugate here. Here, if X equal to X1 to Xn, I need a row, column times a row. Then the result will be a square matrix, n by n, like this. This is a correlation matrix. This one, whether it's a positive definite, I can't remember, but I think similar with the covariance. It should be a yeah, this one maybe also, yeah, it should be also positive definite. This is also positive there. Yeah. Okay, this is a correlation matrix. Then we use a similar way we can describe the Gaussian distribution. The joint Gaussian distribution. We say x equal to x1, x2 until xn, a Bayer normal distribution. Here's a mu and sigma, like this, where I put this column, doesn't matter, where mu equal to mu1, mu2 to some mu n. This is a vector. If you want your column, then you put t here. Okay, and sigma is a symmetric positive definite square matrix. And the density function PDF of x, f x1, x2 until xn of x1, x2 until xn, or equal to, is 1 over square root of let me see, is 2 pi, a determinant of 2 pi times sigma, like this. And here is the expectation, exponential power, exponential power, negative 1/2. This here will be, x1 to xn times that sigma inverse times x1 to xn. Okay, like this. Here is a quadratic form, right? Quadratic form. This is quadratic form. This is the matrix, right? Matrix of coefficients, and the exponential power of negative 1/2 times this quadratic form here. And here is a square root of determinant of this matrix. Oh, this pi will be inside or outside. 2 pi. Sorry, I need to find it. Okay, here. I have it here. Alright. Yeah, it's correct. Oh, it's this one. Yeah, it's this one. Not that. They need to minus that mu. Minus that mu. Should be here. Go to this one. So here will be a row vector, here will be a column vector. If I write in this way, then here's no transpose. Transpose will be here. Transpose will be here. Okay, transpose will be here. Right. If I write x in a column vector, right, that will be transpose here. Yeah. This as a row. Yeah. Okay, it's like this. Like this. It's a row vector, this is column vector, and overall is a quadratic form. Yeah. So we have this. This is density function. And then for the Gaussian distribution, we have some very good result. Actually, this matrix sigma, it is just the covariance matrix. This will be a column vector, this will be a row vector. Okay, here might be a conjugate. All right, yeah. And the mu, it is just the E of x, which is E of x1, E of x2, E of xn. This is the mu. And furthermore, suppose x is a Gaussian distribution with this mu and sigma as the coefficients, and we let y equal to ax plus b is another random variable, maybe a vector, right? Ax plus b, this will be a vector. I get y. This y is still Gaussian. It will obey the au plus b with the first coefficient, and this a, then the sigma, then a transpose of okay, so here I need a column. If I write in this way, A is a square matrix and X is a column plus B. Yeah, like this. Okay, I get transpose. Yeah, I use a uniform. Sorry. Here I put the transpose. The mu is a column vector. This is square matrix, doesn't matter. Then the density function. Here I need a transpose. Here I need a transpose. And here might be we have a star depending on its real or complex. If it's real, then here's nothing. And then because this one is already a column, I don't need these. But here I need a. Let me see. Here I need a t. I make this is a row, right? Make this is a row. This is t. And then mu is here. I need a t. This is a column. This is a column. And then okay. Now this is good. Yeah. So we have this. This is a very good result. You start from Gaussian distribution. You perform a linear transform. You times any matrix on x and plus a constant vector b. You have a new random variable. This new random variable, it is still a Gaussian distribution with some different parameters. Alright. Okay. I have a few minutes, but that'll be all for today. Okay. See you next time. Bye bye.